Usually when we analyze a network intrusion, there is uh, a fundamental expectation of forensic permanence.
Right, like leaving footprints in the mud.
Exactly. It's like a break-in at a physical data center. You come in the next morning and, the server rack is pried open, the physical drives are missing, and the access logs show exactly which badge was swiped at what time.
Yeah, it's a mess.
It's a huge mess, but it's a measurable, reconstructible mess. I mean, you isolate the VLAN, you pull the PC caps, and you just start working backward from the point of impact.
Because there's a chronological breadcrumb trail, we heavily rely on the assumption that malicious actions generate persistent state changes.
Right.
Files written to disk, registry keys modified, firewall rules altered. The entire incident response playbook is basically built on categorizing those state changes.
But when you step into the world of modern software supply chains, that baseline assumption just completely disintegrates.
It really does.
I mean, imagine someone poisons a municipal water supply right at the treatment plant. Millions of people drink it. But the poison is biochemically engineered so that the exact millisecond it's exposed to the reagents we use to test water purity.
It just vanishes.
Right. It evaporates into harmless oxygen. You know your infrastructure is compromised. You know data is bleeding out. But every telemetry dashboard and static analysis tool reports a completely pristine environment.
It's the definition of a forensic nightmare. The telemetry isn't just failing to detect the anomaly. The anomaly is actively using the telemetry's own execution environment to cover its tracks.
It's wild. We are looking at a situation that is actively forcing enterprise security teams to rewrite their incident response playbooks from scratch.
Oh, absolutely from scratch.
So today is April 13th, 2026, and just 2 weeks ago, spanning the window of March 30th to the 31st, the software development ecosystem experienced a tectonic shift.
Yeah, that's not an overstatement.
For today's deep dive, we are unpacking a leaked threat intelligence presentation titled PoisonChain.pptx. It details a catastrophic supply chain compromise of the Axios NPM package.
The big one.
Yeah, and it outlines the automated incident response framework, which is also named PoisonChain, that was built to mitigate the fallout.
And we really have to establish the sheer gravity of Axios as the target here. I mean, for you listening, if you were building a modern web application or a mobile app backend or even an internal CLI tool, you are almost certainly using Axios to handle HTTP requests.
It's everywhere.
Right. It handles the promise-based asynchronous data fetching that essentially powers the modern interactive web. We're talking tens of millions of weekly downloads.
Wow.
So compromising it isn't just breaching a single company, it's pushing a master key into the build pipelines of half the Fortune 500 simultaneously.
Which makes the methodology of this attack so chilling. It wasn't a brute force attack on the registry, it was a surgical strike.
Highly targeted.
Yeah, designed to weaponize the developer's own installation process, detonate in memory, and completely erase its own intent.
It's brilliant in a terrifying way.
So let's trace the execution chain from the very beginning. To poison the water, you first need unrestricted administrative access to the treatment plant.
Right.
According to the PoisonChain intel, this initiated with the compromise of a core Axios maintainer. The attackers successfully published 2 malicious versions, 1.14.1 and 0.300.4.
And those specific version numbers are critical to understand.
How so?
Well, they didn't bump the major version. By publishing a minor patch update like 1.13.1 and an older legacy branch update like 0.30.4, they're exploiting the semantic versioning syntax.
Oh, like the caret or tilde characters in a package.json file?
Exactly. Most automated CI/CD pipelines are configured to automatically pull minor or patch updates during a fresh build.
Right, to ensure they have the latest security fixes.
Yeah, so the pipelines are doing exactly what they were designed to do. They pull the update automatically without human review.
Right, the system is working as intended, just against itself. But here is the technical pivot that caught my attention. The maintainer's disclosure explicitly noted that they were fully compliant with NPM's security mandates.
They're doing everything right.
Right. Their account had a hardware-backed two-factor authentication enabled. Now, the source states the attackers abused legitimate publishing rights from the compromised machine following a targeted social engineering attack.
Yes.
Wait, if 2FA was on, how did this happen? It feels like we're always told 2FA is the ultimate shield. If the attacker is operating remotely and the hardware key is sitting on the maintainer's desk in California.
They aren't attacking the authentication flow.
Right.
They're attacking the authorization state. We
Yeah.
have to differentiate the initial identity verification from the subsequent session management.
Okay, break that down for me.
Sure. When the maintainer authenticates to the NPM registry via their CLI, they provide their credentials, and they tap their YubiKey.
Yeah.
The NPM registry validates that cryptographic challenge and responds by issuing a highly privileged session token. It's usually a bearer token stored in the local .npm.rc file right in the user's home directory.
So the malware on the endpoint doesn't need to spoof the hardware key or intercept an SMS?
Nope.
It just waits for the developer to authenticate normally, and then it quietly reads the .npm.rc file.
Or it extracts the active session cookie from the browser's local storage database.
Yeah.
It's basically riding the coattails of an already validated session.
Wow, so it just hops in the passenger seat once the engine is already running.
Precisely. For you listening, think about your own work devices right now. If someone had silent userland access to your laptop, what trusted systems could they access without ever needing a password?
That's a scary thought.
If the attacker has execution privileges on that endpoint, they operate with the exact same permissions as the developer.
So all the physical security in the world doesn't matter if the machine itself is compromised.
Exactly. Like on a Windows machine, even if the browser encrypts those session cookies using Deep API, the data protection API, the malware running under the developer's user context can just call the crypt-unprotect data API and decrypt the SQLite database instantly.
Instantly.
Yeah. The perimeter is no longer the network gateway or the identity provider. The perimeter is the endpoint's memory space.
And once they ripped that publishing token, they had the keys to the castle. They authenticated to the registry API and pushed the malicious payloads.
They were officially in.
But they didn't directly embed the malware into the core Axios source code, did they?
No, that would be too obvious.
Right. If you look at the diff for Axios 1.1.1, there's no giant block of obfuscated C2 logic. Instead, they weaponized the dependency tree.
A much stealthier approach.
They injected a completely new requirement, a package called PlainCrypto.js at version 4.2.1.
Which is an absolute masterclass in blending into the noise.
Yeah, I mean, modern JavaScript projects often have dependency trees that are thousands of packages deep.
Tens of thousands sometimes. And a package named PlainCrypto.js sounds like a completely mundane foundational polyfill.
Right. No developer reviewing a massive dependency resolution log is going to manually audit a cryptography utility that appears to be pulled in by a network client.
Never. You'd never notice it.
But PlainCrypto.js is the Trojan horse, and its execution mechanism relies entirely on NPM's lifecycle scripts. Specifically, the postinstall hook.
The infamous postinstall.
Right. The moment a developer or, a Jenkins build node runs npm install, the package manager downloads Axios, resolves PlainCrypto.js, pulls it down, and then automatically executes node setup.js without any human intervention.
The postinstall hook is an incredibly powerful and incredibly dangerous legacy feature.
Why does it even exist if it's so dangerous?
Well, it was originally designed to allow native C++ bindings, like Node SAS, to compile themselves locally against the specific architecture of the machine downloading them.
Oh, that makes sense.
Right, it has a legitimate purpose.
Yeah.
But it inherently grants arbitrary code execution privileges simply by virtue of downloading a file.
Just by downloading it. So setup.js executes. This is the dropper. The Intel report dives into the obfuscation techniques here, and it's fascinating.
It's definitely not your standard script kiddie obfuscation.
No, it's not just a simple base 64 encoded string. The payload was encrypted using an XOR cipher.
Yeah.
The key was order_7077, but they added a positional modifier, a per-character offset of 7 times I squared modulo 10.
Let's break down why an attacker adds an algebraic calculation into their deployment script.
Oh, why the math?
When a new package is published, it is immediately ingested by static analysis engines, security vendor honeypots, and AST abstract syntax tree parsers.
Because everyone's watching the registry.
Right. These tools are looking for known malicious signatures or suspicious entropy, like hard-coded IP addresses or domains.
Right. So if you just have fetch sfrclack.com port 8000 in the plain text, the static analyzer flags it in milliseconds.
Exactly. So they encrypt it. But the security vendors know this, so their parsers are designed to dynamically evaluate simple obfuscation.
Oh, so the scanner will try to decode it on the fly.
Yes. If they see standard base 64 decoding, the analyzer just runs the decode function in a sandbox, reads the output, and flags it.
Ah, I see.
So by introducing a polynomial time complexity calculation, the I-squared modulo 10, the attacker forces the automated scanner's regex engines and lightweight AST parsers to consume significantly more CPU cycles.
Wait, so they are essentially inducing a micro-denial of service attack against the scanner itself?
Precisely. Enterprise scanning pipelines process thousands of packages a minute. They have strict timeout thresholds.
Because they can't slow down the developer's build.
Exactly. If a script takes too long to evaluate dynamically, the scanner often defaults to a pass to avoid holding up the CI/CD pipeline. The math isn't meant to be cryptographically secure against a human reverse engineer.
It's just designed to exhaust the computational budget of an automated sandbox.
Just buying them the 60 seconds they need to fetch the real payload from sopilotclack.com, port 8000/610233.
Unbelievable. But, you know, the most insidious part of this dropper isn't even the math.
No, it's what comes next.
It's the cleanup phase. According to the PoisonChain presentation, the moment setup.js successfully fetches the second stage payload, it deletes itself from the disk.
Entirely.
And then it dynamically swaps out its own package.json metadata file, replacing it with a harmless stub that claims to be version 4.2.0 with no postinstall hook.
This is where the standard paradigm of software auditing just collapses.
I mean, it's like a burglar who picks your lock, steals your valuables, but then vacuums your living room and leaves a mint on the pillow so you don't realize you've been robbed on a casual inspection.
That's a perfect analogy.
But practically, how does it even do that while the process is actively running? You're executing a node script that is modifying the very directory it resides in.
Well, in a Unix-like environment, when a process executes a file, it holds a file descriptor in memory. The process doesn't actually need the physical file to remain untouched on the disk to finish its current execution context.
Oh, wow.
Yeah, the malware can issue a system call to unlink the setup.js file, effectively removing the directory entry, while the active memory process continues to run just fine.
That feels like a glitch in the matrix.
It really does. And then it overwrites the package.json file using standard asynchronous file I/O operations.
So it's actively rewriting the historical record of its own installation.
Yes, and the implications for vulnerability management are catastrophic here. Security teams rely heavily on commands like npm audit, or tools that parse the package-lock.json and the physical node modules directory to generate a software bill of materials.
Right, to see what's actually running in production.
But if a security engineer runs an inventory check an hour after the compromise, the system scans the plain crypto.js folder, reads the modified package.json, sees version 4.2.0 with 0 lifecycle scripts, and reports a clean bill of health.
So the evidence of the attack is systematically dismantled by the attack itself.
Exactly. The dropper creates a localized reality distortion field.
It executes, pulls down the real malware, and then just vaporizes. Which brings us to the actual payloads.
The fun part.
Yeah, the setup.js script didn't just pull down a generic piece of malware. It queried the host's environment variables to determine the underlying architecture, and then it delivered one of 3 distinct remote access Trojans.
3 different RS.
This multi-platform capability demonstrates a terrifying level of resource allocation. Let's look at the macOS payload first.
Sure, macOS environments are heavily prevalent in front-end and full-stack development, making them a really high-value target for this specific NPM vector.
Right. If the victim was running a Mac, the dropper pulled down a 657 kilobyte macOS plus binary.
Which is pretty hefty.
Yeah, and it established persistence by placing itself in /library/caches/com.apple.mond. And it was configured to beacon out to the command and control server every 60 seconds.
Like I said, 657 kilobytes is a substantial binary for second-stage payload. It indicates a fully statically linked executable, likely containing really robust network communication libraries and local enumeration tools.
Why did they choose the library caches directory?
That's a classic evasion technique. Modern macOS utilizes System Integrity Protection, or SIP.
Oh, right, SIT.
Yeah, which locks down core system directories even from root users. However, caching directories are historically permissive because applications constantly need to write temporary data there.
So it bypasses the strict SIP enclaves by hiding in the system's scratchpad.
Exactly. And to achieve that 60-second beacon, it likely dropped a custom property list, file-a-dot list into the user's // library/launch agents directory.
Hooking into the OS.
Right. Hooking into the macOS launch process to ensure the malware automatically restarts if the process is killed or the machine reboots.
Now contrast that heavy, persistent C++ application with the Linux payload.
It's completely different.
Completely. If the dropper detected a Linux environment, it went in the complete opposite direction. It downloaded a tiny 12 kilobyte Python script, dropped it into the temporary directory at /tm/lled.py, and executed it in the background using NoHub.
Yeah.
But the most striking detail in the Intel report is that this payload had 0 persistence mechanisms. If the Linux machine restarted, the malware was permanently gone.
Well, we have to analyze the operational context of Linux in a modern enterprise development pipeline.
Okay.
While some back-end developers do run desktop Linux, the vast majority of Linux hits for an NPM package are going to be automated CI/CD runners.
Like ephemeral Docker containers.
Exactly. Containers spun up by Jenkins, GitLab CI, or GitHub Actions.
They are essentially disposable operating systems.
Precisely. A Jenkins worker node might spin up, pull the repository, run npm install, compile the application into a static binary, upload the artifact, and then immediately terminate the container.
Wow. So the entire life cycle of that machine might be, what, 5 minutes?
5, maybe 10 minutes. The attackers understand that persistence is irrelevant here. If the machine ceases to exist, a cron job or a system service is completely useless.
So they just need it to run now, steal the environment variables, and get out before the container is destroyed.
Exactly. And using a Python script is a textbook living off the land technique.
Because Python is already there.
Right. Almost every standard Linux build image, whether it's an Alpine container or an Ubuntu runner, has a Python interpreter natively installed to handle standard build utilities.
And what does NoHub do in this context?
By leveraging NoHub, the script detaches from the current terminal session. That ensures that even if the primary npm install process finishes and the shell closes, the Python script continues running in the background for those critical few minutes before the container is reaped.
That is so efficient. But wait, the threat intel notes a critical flaw here?
Ah, yes. Bug.
The Linux payload had a bug. A specific command within the script, pan-inject, failed to execute due to a Linux porting error. How does a group this advanced push a payload with a bug in it?
It's an incredible detail because it humanizes the adversary. No matter how sophisticated the operational security, they are still software engineers dealing with cross-platform compatibility issues.
They still make typos.
Exactly.
Yeah.
The pan-inject command strongly implies they were trying to execute a portable executable injection.
Which is a Windows thing, right?
Right, a technique primarily designed for Windows, but they tried to map it within a Linux memory space.
Mm-hmm.
It suggests they were reusing core C2 functionality across their tool set and just failed to properly QA the Linux-specific translation of those system calls.
It shows they were operating under a tight deadline. They pushed the code despite the failing tests.
Ship it.
Right. Ship it, we'll fix it in production, even if production is malware, which transitions us perfectly to the third operating system target, Windows.
The hardest nut to crack.
For sure. If you were developing on a Windows machine, you didn't get a heavy binary or a Python script. You got a fileless PowerShell loader utilizing .NET Reflection. The initial hook was placed at %program data %/w.exe with a registry run key for persistence.
The Windows ecosystem presents the most hostile operational terrain for a malware author, primarily due to the maturity of the anti-malware scan interface, or AMSI.
And the deeply integrated endpoint detection and response platform.
Exactly.
If you drop a compiled executable onto a modern Windows disk, Defender is going to immediately halt execution, sandbox it, and analyze the import address table.
Without a doubt. File-based deployment on Windows is incredibly noisy these days, so they utilized a fileless execution chain.
How does that work?
The initial payload is likely a heavily obfuscated PowerShell one-liner that reaches out to the C2 and downloads a compiled .NET assembly. But instead of saving that assembly to the disk, it uses the system.reflection.assembly.load method.
It loads the binary array directly into the active RAM space of the PowerShell process.
Yes, the actual malicious executable never touches the physical hard drive. It exists purely as volatile memory.
That is insane.
Because the binary is never written to disk, traditional file-scanning antivirus engines are completely blind to it. And by leveraging .NET Reflection, they can dynamically invoke methods within that malicious assembly, completely bypassing the standard Windows API hooking that EDR solutions use to monitor suspicious process creation.
It's literally a ghost in the machine.
A very dangerous ghost.
And for persistence, they rely on the Windows registry. Modifying a run key under HKCU's software Microsoft Windows current version run ensures the PowerShell loader executes every time the developer logs in.
Simple but effective.
And that wt.executable is likely just a hijacked legitimate binary, right?
Yeah, perhaps a renamed Windows terminal executable.
Yeah.
It's just used to quietly bootstrap the PowerShell process without raising suspicion.
So for everyone listening, just think about this. No matter what OS you are using right now to listen to this deep dive, there was a custom weapon built specifically for your architecture.
A heavy Mako binary for Macs, a volatile Python script for Linux, and a fileless .NET assembly for Windows.
3 entirely distinct code bases, interacting with 3 entirely different operating system APIs.
But, and this is the crazy part, they were all communicating with the exact same infrastructure.
Right. The PoisonChain report outlines the command and control architecture. The primary C2 was hosted at sfrclack.com port 8000 with a fallback domain of callanrwise.com.
And regardless of whether the victim was a Mac developer, a Windows developer, or an ephemeral Linux container, the C2 server utilized a unified shared command set.
The commands were kill, run script, rundir, and painject.
This highlights the immense operational maturity of the group orchestrating this attack.
How so?
Well, if you are an operator managing a campaign with potentially thousands of compromised endpoints, the cognitive load of tracking the underlying OS for every single target is unsustainable.
You don't want to query the victim, see it's a Linux box, and then try to remember to send bash syntax for directory enumeration, and then switch to PowerShell syntax for the next victim.
Exactly. You'd make mistakes constantly. So you build an abstraction layer. The attacker just issues the rundir command from their centralized dashboard.
Oh, I see.
The C2 infrastructure sends that command down the WebSocket or HTTP polling channel. The local agent, whether it's the Mac binary, the Python script, or the .NET assembly, receives rundir, interprets it, and executes the native system calls for that specific OS.
And then it just returns the directory listing in a standardized JSON format back to the C2.
Right. It's enterprise-grade malware orchestration. It really is.
But amidst this enterprise-grade orchestration, there is an anomaly that completely defies logic.
The neon sign.
The neon sign. When these highly sophisticated RATs beaconed back to the C2 server over HTTP, they used a specific user agent string to identify themselves in the request headers.
Oh, yeah.
They used Mozilla /4.0 compatible, Mengzi 8.0, Windows MT 5.1, Trident /4.0.
Which is the Internet Explorer 8 string running on Windows XP.
In 2026, think about the absurdity of this. You have a cutting-edge fileless .NET payload executing in memory, bypassing AMSI, and when it makes a network request out to the internet, it puts on a digital name tag that says, "Hello, I am Internet Explorer 8.
It's hilarious, honestly.
If I am running a network proxy or a next-gen firewall, an IE8 user agent originating from a modern macOS developer laptop or a cloud-native Linux container isn't just an anomaly, it is a screaming siren.
Yes.
It's like someone trying to sneak into an exclusive 2026 nightclub wearing full 18th century Victorian attire. It's meant to blend into legacy traffic, but it sticks out like a sore thumb in a modern environment. Why on earth would they hard-code this specific string?
It is the most heavily debated artifact in the entire Intel report.
I can imagine.
We have to look at the psychology and the operational constraints of threat actors. The primary theory is code regress and operational fatigue.
So laziness.
Essentially. This specific user agent string isn't random. It is a known historical artifact associated with specific malware families dating back a decade.
So the developer writing the network communication model for the RAT just copy-pasted a legacy HTTP request function they wrote years ago and didn't bother to update the header dictionary.
That is the most Occam's razor explanation. In the rush to build 3 distinct payloads for a targeted, time-sensitive supply chain attack, the QA process for network evasion just fell through the cracks. It perfectly mirrors the bug we saw in the Linux package-lock command.
I have to push back on that, though.
Okay, go ahead.
If you are a state-sponsored actor, your entire mandate is stealth. I find it hard to believe you accidentally leave an IE8 string in your cutting-edge Mac malware.
Fair point.
Could this be a deliberate false flag? Like, are they trying to mimic a different, older threat group to confuse attribution?
It's a highly plausible counter-hypothesis. False flag operations are standard doctrine in state-sponsored cyber warfare.
Right.
If a threat hunting team at a major tech company spots an IE8 user agent, they might immediately categorize the alert as a low-level legacy commodity malware infection.
Something a script kiddie deployed.
Exactly. Rather than escalating it as an active nation-state supply chain breach, they might just tune out the noise, wipe the machine, and move on.
It's a fascinating gamble, but regardless of the intention behind the user agent, the data it was exfiltrating was catastrophic.
Unbelievably damaging.
Their presentation extensively details the credential exposure surface. The objective of this campaign wasn't simply to maintain access to a few developer laptops. The RATs were designed to systematically pillage the local environment for high-value authentication material.
They wanted the keys to everything else.
They targeted NPM tokens, CI/CD deployment secrets, cloud architecture keys, SSH private keys, and active browser session data.
This is where we see the transition from an endpoint compromise to an enterprise-wide infrastructure breach. A senior developer's laptop is essentially a vault containing the keys to the entire production environment.
Walk me through the mechanics of that harvest. How is the Python script on a Linux-built server finding those cloud keys?
So when an automated Jenkins server runs a build that needs to deploy code to AWS, the DevOps team injects the AWS access key and secret key into the container as environment variables.
Okay, so it's loaded into the environment.
Right. The Python RAT simply executes oz.environ and dumps the entire list of variables directly to the C2 server.
It just scoops them all up.
Yep. And if the payload is on a developer's Mac, it iterates through the /.oz/credentials file, reads the plaintext keys, and pulls the private RSA keys from the /.cesh directory.
And with those cloud keys, the attacker can completely bypass the developer. They don't need the RAT anymore.
Nope, they're done with the endpoint.
They can take that AWS token, authenticate directly to the victim company's cloud infrastructure from their own servers, spin up rogue EC2 instances for crypto mining, or just dump the production S3 buckets containing customer databases.
The blast radius expands exponentially with every second the RAT is active.
Which brings us to the most critical attribution data. Who is organizing an attack of this magnitude?
The whodunit.
Exactly. The PoisonChain presentation references intelligence from Google's Threat Intelligence Group, GTIG. They track this specific activity cluster under the designation UNC1069. Broadly, the security industry refers to this actor as TA444 or BlueNoroff.
Yes.
And the intel explicitly identifies them as a Democratic People's Republic of North Korea state-sponsored group.
A very specific subset, too.
Right. Furthermore, GTIG linked this specific Axios breach to a wider, coordinated campaign tracked as Team PCP, which successfully compromised 4 other open-source projects in March of 2026 alone.
BlueNoroff is a highly specialized nexus within the broader Lazarus Group architecture.
What makes them different?
Well, unlike traditional state-sponsored intelligence units that focus on, geopolitical espionage or military network disruption, BlueNoroff has a completely distinct mandate.
And strictly adhering to the attribution provided in the source documentation, what is that mandate? Why target JavaScript developers instead of defense contractors?
Financial extraction. It's exactly. Given the economic realities and heavy sanctions surrounding the DPRK, these cyber units are tasked with significant revenue generation.
Wow.
The modern financial ecosystem is increasingly decentralized, relying heavily on cryptocurrency, decentralized finance protocols, and the massive tech infrastructure that supports them.
And all of those crypto exchanges, those DeFi platforms, they are all built using JavaScript. They all use Axios.
You got it. By compromising a foundational open-source package, they cast an incredibly wide net. They infect thousands of developer machines and build servers across the globe.
And then what?
Then, they ingest all the stolen credentials, SSH keys, and browser sessions into their back-end infrastructure. They automate the parsing of those logs to identify victims working at high-value financial targets.
So they aren't trying to steal a military schematic.
Not at all. They are looking for the AWS keys that control the hot wallets of a cryptocurrency exchange.
It is an industrialized, algorithmic heist.
That's a great way to put it.
But to pull off a heist of this scale, the timing has to be immaculate. And the timeline detailed in the report is perhaps the most astonishing aspect of the entire incident.
The 3-hour window.
The 3-hour window. The entire compromise, from publication to unpublishing, occurred in an incredibly narrow time frame. The dropper, plain crypto.js, was staged. Then, Axios 1.1.1 was published at 0.21 UTC, Axios 0.30.4 followed at 01.0000 UTC.
And then they were gone.
Yes. The malicious packages were unpublished between 03.15 and 03.151 UTC, less than 4 hours.
It's incredibly fast.
It completely subverts my understanding of malware distribution. I mean, if you burn an incredibly sophisticated 2FA bypass 0-day and you successfully compromise the maintaining infrastructure for one of the the most popular packages on the planet, why would you only leave the trap open for 3 hours?
It seems counterintuitive, right?
Totally. Why not leave it up for a week and infect millions of endpoints instead of a fraction of that?
Because in the modern software supply chain, longevity is a liability.
Oh, because of detection.
Exactly. The global security community researchers, automated dependency scanners, AI-driven anomaly detectors are constantly monitoring packages with the velocity of Axios. If a rogue update sits in the registry for a week, it is mathematically guaranteed that someone will notice the obfuscated XOR logic in plain crypto.js.
And once it's detected, the security vendors immediately issue global blocks. The domains are sinkholed, the IP addresses are blacklisted.
And the entire multi-platform C2 infrastructure the attackers spent months building is burned globally.
Oh, I see.
The burn-down rate of their infrastructure would hit 100% almost instantly. They would lose their entire investment and gain very little actionable data because the industry would rapidly roll back the updates and rotate their credentials.
So it's a precision strike designed to evade the global monitoring apparatus.
Yes, they target a very specific window. 00000 to 03.000 TC is late evening in the Americas and early morning in Europe.
What happens then?
It is the prime window when enterprise automated build systems, the Jenkins servers, the GitHub Actions runners, are scheduled to perform nightly integration tests and dependency updates.
Of course, the cron jobs.
Right. Those headless servers wake up, blindly pull the latest patch version of Axios, execute the postinstall dropper, siphon the environment secrets, and transmit them to the C2.
And then, before the human security engineers even log in for their morning coffee, the attackers unpublish the packages themselves.
By the time the world wakes up, the malicious code is gone from the registry.
They minimize their exposure to researchers while maximizing their exposure to high-value, highly privileged automated environments.
Ruthless efficiency.
But this creates an absolute nightmare for the organizations trying to determine if they were hit. The registry is clean. The malware deleted its own setup.js file. It rewrote its own package.json to look innocent.
The ephemeral Linux containers that ran the build have already been destroyed.
Exactly. How does an enterprise security team even begin to trace the blast radius of an invisible explosion?
And this is the exact crisis that birthed the automated incident response tool detailed in the presentation.
Right, the PoisonChain pipeline. The antidote to the attack.
The antidote.
The presentation outlines a highly specific, highly automated framework built to definitively answer the C-suite's screaming question. Were our systems compromised during that 3-hour window?
And the core philosophy of this tool is distilled into one incredibly profound sentence.
Let's hear it.
Lockfiles show intent. Jenkins logs show execution.
That distinction is so fascinating. It feels like the bedrock of modern forensic analysis in CI/CD environments. You cannot rely on the static state of the code base.
You really can't.
Let's unpack the mechanics of that. If I'm a security engineer, my first instinct is to scan my company's repositories for package-lock.json files and grep for Axios 1.1.1 or plain crypto.js. If I find it, I assume we are breached. Why is that insufficient?
Because the lock file only represents the desired state of the application as defined by the package manager. It is a blueprint.
A blueprint.
Yes. It says, the next time this project is built, please download these specific versions. It proves the project had the intent to pull the malicious code.
But intent doesn't equal execution. What if the project hasn't been actively built in 6 months?
Exactly. The lock file might be updated by an automated dependency bot, like Dependabot, opening a pull request. The malicious version is documented in the PR, but no server actually ran npm install.
If you declare a breach based purely on the lock file, you generate an unmanageable volume of false positives.
A massive volume. You force hundreds of developers to rotate their credentials and halt production for projects that were never actually infected.
Which cost the business millions.
Exactly.
Yeah.
And conversely, you might have a project without a strict lock file that dynamically pulled the bad version during that 3-hour window, executed the malware, and then pulled a clean version an hour later.
The lock file's the blueprint, but the Jenkins log, the raw historical console output of the build server, that is the security camera footage.
Yes, that is the proof.
It definitively proves that at 02.15 UTC, the server actually fetched the package, extracted it, and ran the lifecycle scripts.
And the PoisonChain tool operationalizes this philosophy through a 6-stage automated architecture. It is designed to compress what would normally be weeks of manual log parsing into a 2-hour automated sprint.
Let's trace this pipeline. Stage 1 is canister worm analysis.
Right.
This implies pulling the initial threat intelligence, likely grabbing the specific IOCs indicators of compromise from an internal vulnerability database or a vendor API. It establishes the baseline signatures for plain crypto.js and the known C2 domain.
It defines the parameters of the search.
Then we move to stage 2, Bitbucket full scan. The tool programmatically authenticates to the organization's version control system and scans potentially tens of thousands of repositories.
It is looking for the Lockfiles. It maps the intent.
It creates the initial suspect list, which projects were theoretically exposed.
And then it executes stage 3, which is frankly brilliant.
Oh, this is my favorite part. Fetch committers. It cross-references the exposed repositories with the organization's identity and access management systems, essentially performing an automated HR statting check. Why is verifying the employment status of a developer a critical step in a malware response pipeline?
Because the ultimate objective of the attacker is credential theft. If PoisonChain identifies a repository that was exposed to the malware, you must assume the active tokens associated with that repository are compromised.
Naturally.
But in an enterprise environment with high turnover, developers change teams, migrate between departments, or leave the company entirely.
And their legacy tokens might still be active in the system.
Precisely. If the tool cross-references the repository owner and discovers that the lead developer resigned 3 months ago, but their personal access token is still actively pushing code to that repository,
You have a massive, immediate red flag indicating lateral movement by the attacker.
it's exactly. Or, alternatively, if the developer is actively employed, the system automatically pulls their contact information, so the Security Operations Center can immediately isolate their workstation and enforce a credential rotation.
You completely eliminate the hours wasted asking around Slack trying to figure out who owns the legacy billing API.
It automates the human triage.
Which brings us to stage 4, the Jenkins scan. This is where the tool correlates the intent from Bitbucket with the execution logs from the build servers.
This is the computationally heavy lifting.
I bet.
The pipeline interfaces with the Jenkins API, pulling down the raw console logs for every build executed during the critical time window across all the suspect repositories.
And it's parsing massive, unstructured text files looking for specific forensic markers. The presentation notes that despite the malware's rigorous self-cleanup, it leaves breadcrumbs.
It can't clean up everything.
The primary marker is the presence of the node modules /plain crypto.js /directory path in the build logs. Even though setup.js deleted itself and rewrote the metadata, the NPM client still logged the extraction of the physical directory to standard output.
It's the digital equivalent of spraying luminol at a crime scene. The attacker wiped the blood off the floor, but they couldn't rewrite the security camera log that recorded them walking into the room.
The Jenkins console output is immutable relative to the container's execution context.
Exactly.
PoisonChain also scans for the platform-specific artifacts, like the Mac file path /library/caches/com.apple.act.mond. If a developer ran the build locally and pushed their terminal output, or if a macOS build node was utilized, that specific path acts as a definitive indicator of compromise.
The pipeline then flows into stages 5 and 6. Report Axios by team, and preserve evidence.
The cleanup phase.
Right. It takes this massive chaotic data set, synthesizes it, and generates targeted, actionable JIRA tickets or dashboards for each specific engineering manager, outlining exactly which of their systems need credential rotation.
And crucially, it locks down the raw forensic data in a secure, immutable storage bucket, so the threat actors cannot tamper with the evidence post-discovery.
It is an incredible piece of security engineering. It turns sheer panic into a prioritized to-do list.
However, there is a fundamental limitation to this architecture. The PoisonChain pipeline assumes you are operating in a unified, hyper-connected corporate environment.
Which isn't always the case.
Right. It requires programmatic API access to Bitbucket, Jenkins, the HR databases, and the security enclave simultaneously. What happens if a specific engineering team operates in a completely isolated environment?
You are addressing the reality of decentralized infrastructure, particularly in highly regulated sectors.
Which is why the threat intelligence package includes Section 7, Do-It-Yourself Defense. The presentation provides a standalone forensic toolkit, a zip file named jenkinsscankit.zip.
A lifesaver for those teams.
The documentation specifies that it requires 0 external dependencies, relies on a simple .n file for configuration, and can execute entirely offline by running Python 3 jenkinsscan.py.
This is a vital democratization of the forensic capability.
The documentation explicitly highlights its utility for air-gapped environments.
Hmm.
Now, for the sake of clarity, for anyone listening who might not know, an air-gapped network means there is a literal physical gap of air between the local network and the public internet.
No Ethernet cables, no Wi-Fi, no external routing.
Right. These environments are typically reserved for highly classified defense networks, core critical infrastructure like power grids, or deeply sensitive financial trading algorithms.
Correct.
If an environment is completely severed from the internet, it cannot query the NPM registry. So how could an NPM supply chain attack possibly breach an air gap? Logically, the Axios malware can't traverse the physical space to reach the isolated Jenkins server. Why would a North Korean APT group even factor air-gapped systems into their calculus?
Because the physical isolation of the server hardware does not isolate the human development lifecycle.
What do you mean?
An air-gapped network still requires software updates, dependency management, and new code. To facilitate this, organizations utilize secure bridging mechanisms.
How does the code actually cross the gap?
The most common vector is a secure internal registry proxy, such as an isolated instance of JFrog Artifactory or Sonatype Nexus.
Okay.
This internal registry periodically syncs with the public NPM registry through a highly scrutinized, strictly controlled one-way data diode. The public registry pushes the approved updates across the diode into the isolated network.
So if the internal proxy initiates its synchronization cycle during that critical 3-hour window,
The internal proxy will pull down Axios 1.1.11 and plain crypto.js. It pulls the malicious packages across the air gap, assuming they are legitimate updates.
oh wow.
The isolated Jenkins server then triggers an internal build, queries the internal proxy, pulls the packages, and executes the postinstall dropper.
The malware detonates inside the secure enclave?
Exactly. Now, the malware cannot complete its primary objective immediately. It cannot beacon back to swarclack.com because there is no outbound internet routing. The DNS resolution will fail.
But the dropper still executes, the payload still loads into memory.
Yes, the payload executes. It archives the highly classified internal environment variables, the proprietary source code, or the internal SSH keys, and it stores them locally.
And then what? It just sits there.
It establishes persistence and waits. It waits for a developer to plug in a USB drive to transfer logs, or it waits for an internal configuration error, or it attempts to pivot through a compromised internal asset that does have a heavily filtered outbound connection. The air gap is breached from the inside out.
That is deeply unsettling. And in that scenario, the centralized PoisonChain pipeline is completely useless. You cannot pipe highly classified air-gapped Jenkins logs out to a central corporate security server connected to the internet.
That would completely violate the core security protocols of the enclave.
Which is exactly why the standalone Jenkins scan kit is paramount. The isolated engineering team can copy the Jenkins scan kit.zip onto a secure thumb drive, walk it into the clean room, deploy it locally on the isolated master node, and run the Python script against their local logs.
And that definitively proves whether the internal proxy synced the malicious payload without ever transmitting a single byte of telemetry back to the corporate network.
It empowers the isolated operators to conduct their own forensic validation. If you, the listener, are responsible for managing a Jenkins instance, regardless of whether it's sitting on an air-gapped military network or just a private server under your desk, this intelligence gives you the exact methodology to verify your historical integrity.
Download the kit, configure the local URL, execute Python 3 jenkinsscan.py, and analyze the output in reports/jenkinsscanresult.json.
It transitions the threat intelligence from an academic exercise into a deployable tactical asset. We have mapped an incredible sequence of events today.
We really have. It's a lot to take in.
The sheer scale and architectural complexity of this attack fundamentally challenge how we view software security. We are looking at a highly sophisticated state-sponsored actor, attributed as the DPRK-linked BlueNoroff, who bypassed hardware 2FA not by breaking the cryptography, but by hijacking the authorization state of the endpoint itself.
They leveraged that access to compromise Axios, a structural pillar of the modern web.
They engineered a dropper that utilized polynomial mathematics to exhaust automated static analysis engines. They hijacked the NPM lifecycle scripts to execute code without developer interaction.
And they deployed tailored cross-platform malware, abusing macOS caching directories, living off the land with Linux Python scripts, and utilizing .NET Reflection to bypass Windows AMSI completely.
They exfiltrated critical cloud infrastructure keys back to a unified C2 server, utilizing legacy user agents to potentially spoof attribution or simply bypassing noisy legacy monitoring.
And they executed this entire devastating campaign, from the initial publication to the final unpublishing and the self-destruction of the metadata, in an agonizingly brief 3-hour window.
A surgical strike aimed directly at the automated CI/CD pipelines of the world's largest tech companies.
It is an absolute masterclass in exploiting the implicit trust we place in our automated tooling.
Which forces a very uncomfortable philosophical reckoning for the software industry. And this brings us to the lingering concept we need to leave you with today.
The big question.
Right. The entire modern digital ecosystem, the applications handling your banking, the back-end services managing logistics grids, the secure communication platforms, they are all built on the foundational axiom of open source security. Given enough eyeballs, all bugs are shallow.
It is the assumption that because the code is public, it is inherently subject to rigorous peer review. We trust the dependency tree because we believe the community is watching.
But this attack architecture completely subverts that axiom. If the malicious execution occurs entirely within the volatile, split-second lifecycle of a post-install script, and if the payload dynamically unlinks its own files and overwrites its own package.json metadata before a human engineer ever has the opportunity to review the disk state, then the eyeballs are useless.
You cannot review code that fundamentally ceases to exist before the review process begins. We are relying on static analysis to catch dynamic, self-erasing threats.
We are looking for shattered glass, but the glass was biochemically engineered to melt the exact moment it hit the floor, which leaves us with the most terrifying question of this entire deep dive.
Okay.
If this specific group managed to orchestrate this level of invisible compromise for 3 hours in March, what else has already slipped through? What other self-deleting packages have detonated inside our build servers, quietly archived our cloud secrets, rewritten their own history, and vanished back into the ether without triggering a single alarm?
It suggests that the integrity of our historical builds is a matter of faith rather than verifiable fact.
It certainly makes you look at every single line of your automated deployment logs a little differently. You run the NPM audit, the telemetry reports a pristine environment, and it says the water is perfectly safe to drink. But you know the poison evaporates on contact. You still have to take a drink.
A deeply sobering reality.
Thank you for joining us on this deep dive into the Axios compromise. We encourage you to analyze your own build pipelines, question the static state of your Lockfiles, leverage the Jenkins logging mechanisms, and as always, stay profoundly curious.